Hello, everyone. Thank you so much for joining me today. We'll be solving our mock exam in preparation for the real one. The first problem reads consider the function f of x equals x squared times e to the x. Find all intervals where the function is increasing and the intervals where it is decreasing, as well as the coordinates x and y of any local min max points. You do not need to graph the function. Excuse me. So let's see how we actually proceed. Remember, when you're taking the intervals where a function is increasing and decreasing, and you want to find anything to do with its max min points, what you got to do first is derive the function. What we're given out of the box is the function's formula. You want to find its derivative. So how do we find the derivative? Well, we have a product of two things, x squared times e to the x. So let's derive the function using the product rule. So let's derive the function using the product rule. This is just literally me plugging into the product rule. So x squared prime times e to the x as is plus x squared times e to the x prime. Now, let's actually see how we can proceed. What's the derivative of x squared? This one, it's just 2x, so 2x times e to the x, logical. And this one, x squared plus x squared times, what's the derivative of e to the x? It's e to the x. E to the x stays the same thing. E to the x is in fact its own derivative. That's why it's one of the reasons why it's special. So f prime of x is equal to 2x plus e to the 2x times e to the x plus x squared times e to the x. Okay, that's good. Now, let's see how we can actually proceed with this. It's good because we want to actually, it's good to actually factorize and simplify to the extent that it's possible, because what we're going to be doing is not leaving this as our final answer. The goal is to plug stuff into this and do stuff with this computationally. So let's actually factor things out to the extent that it's possible, just to make our lives easier when things are coming along. So we have the e to the x as a common factor, and x and x squared being x times x, have the x as a common factor. So x times e to the x multiplied by 2 plus x. That's basically the factorized version. Okay, now the next step logically is to solve for the derivative being equal to 0. We want to punctuate the interval of the real line to actually find the subchunks. Think of it as like putting commas into place. So in this case, our commas are going to be the critical points where the derivative is in fact 0. So solve f prime of x equals 0 for x, and that's going to be x times e to the x multiplied by 2 plus x. That is actually equal to 0. And you got a product of two things, this multiplied by this multiplied by this. This in fact is the product of three things, which must be 0. How do we make the product equal to 0? What you got to do is to actually find the possibility of each term being 0. You need 0 multiplied by something to produce a 0. Okay, so 2 plus x is being set to 0. So that logically means x is equal to negative 2. Okay, the other possibility is e to the x is 0, which doesn't actually work. It doesn't actually happen because the exponentials are always positive in our course. So e to the x is always positive, never 0. So that's discounted, always positive, never 0. Beautiful. And last but not least is x, and x is going to be x equals 0. There's nothing really to solve. So you got two possibilities, negative 2 and 0. Okay, let's actually draw ourselves a little number line. For this one, let's put x is equal to negative 2. Draw our little column. And for this one, it's x is equal to 0. Let's actually find the chunks. So let's actually... let me actually just make this table more sensible looking. So in this case, that's this. And in this case, I just want to leave myself enough room. So for x is equal to negative 2, the interval to the left of it is x is less than negative 2. The interval between is negative 2 and 0. And the interval on the right is x is greater than 0. So for the far left interval, that's going to be x is equal to x equals negative 3. That's the simplest value we're going to choose, such that it's easy to work with and easy to plug in. Logically, this is easier than, say, taking negative 2.5 or negative 10. This is basically standard operating procedure from class, where we take an interval and we take the simplest dummy test value that we want to plug into the derivative to see if it's positive or negative. Okay, So f prime of negative 3, let's see what we get. We get negative 3 times, what is that? I'm literally plugging into this factored version. So negative 3 times e to the negative 3 times 2 plus, or 2 minus 3, because it's 2 plus x and x is negative 3. Okay, now let's see what we got. We got negative 3 times e to the negative 3 times negative 1. Negative 3 times negative 1 is 3, and so that's 3 times e to the negative 3. Now, as you'll recall, e is, and the exponential is always positive in this class. Exponentials always are. This is logical considering e is a special number that's approximately 2.71 something. So 2.71 something to any power is always going to stay positive. So this is positive, and so is this. So the product of two positive things will logically be positive. And so that's going to be increasing. If the derivative is positive, logically your function is increasing. That's what we learned in class. The interval for x is between negative 2 and 0. We're going to be choosing x is equal to negative 1. So f prime of negative 1. What am I going to be plugging into? The derivative in factored form. That makes life easier when you want to plug stuff into it. So literally plugging into this. So negative 1 times e to the negative 1 times 2 minus 1. Okay, it's actually 2 plus minus 1, so 2 plus x. But since x is negative 1, so it's 2 minus 1. So in this case, f prime of negative 1, that's actually going to be equal to what? Negative 1 times e to the negative 1 times 1. 2 minus 1 is 1. Anything by 1 multiplied by 1 is remains unchanged. So negative 1 times e to the negative 1, that's negative e to the negative 1. E to the negative 1 is an exponential, so it's positive. Along with a negative, that makes a negative. So this is negative. So I believe that's going to be decreasing. Oh, let me actually, like this. Now, what about the last one? The last one, we want to pick the simplest number on the interval x is greater than 0. Let's actually choose the number x equals 1. And that's the simplest, one of the simplest numbers in the universe, and in this case, it actually fits into the interval greater than 0. So might as well choose the simplest answer you can, the simplest number you can to make your life a whole lot easier. F prime of 1 is going to be 1 times e to the 1 times 2 plus 1. Okay. Well, 1 times anything, that's going to leave it unchanged. This 1 times doesn't actually do anything. Anything times 1 remains unchanged. 2 plus 1 is 3, so you got e times 3. And so this is positive, and so is this. So the final answer is going to be positive. And so it is increasing like this. Okay? We found the intervals where the function is increasing and decreasing. And let's actually find the minimum and maximum points. So in this case, if you look at this column, to the left of it, the function is increasing like this, and to the right, it's decreasing. This seems to be a maximum. That's a peak, not a valley. What about this one? This one is decreasing, and then it's increasing. This one seems to be a valley, not a peak, so it's a minimum. So we know for a fact that x is equal to negative 2. Good. That's a maximum. And we know that x equals 0 is a minimum. Now, the instructions specifically stated that we need to find the x and y coordinates of the min and max. We found the x coordinates, that's half the job done. How do we actually find the y coordinate? If you'll recall, another way of writing the function is y equals f of x. So y equals f of x is equal to x squared times e to the x. That's, e to the x. That's basically how we write this function. So in particular, if you want the y coordinate of the point x, any x, you plug that into the function. So y is equal to f of negative 2, and that's going to be equal to negative 2 squared times e to the negative 2. What's negative 2 squared? That's 4. That's 4 times e to the negative 2. No one actually expects us to expects you to know what that is decimally without a calculator, a scientific calculator, obviously. So in this case, this is a perfect final answer, perfectly valid. Answers in terms of pi and e are perfectly valid, and they do not need to be changed. That's not indicative that you've done something wrong. Far from it. This answer is perfectly correct. What about this one? Y of equals f of 0. That's 0 squared times e to the 0. Okay, well, 0 squared is 0, so that's 0 times e to the 0. Sorry. Oh, that was meant to be a little multiplication dot. So 0 times e to the 0, anything times 0 is going to stay 0. So we might as well say 0 times anything is 0, and so we found the y. So we actually found the x and y coordinates for the max, and we found the same for the min. And that is the conclusion of the first problem. This is literally taking the problem and asking and providing the author everything they asked for. increasing and decreasing intervals denoted by the table, the arrows in the table, and x and y coordinates of the max and min. It just so happens in this case the function had a max and a min. Okay, this concludes the first problem. Let's actually move on to the second problem. Okay, let's move on to problem 2. Find the absolute maximum and absolute minimum values of the function f of x equals 2x cubed minus 3x squared minus 12x plus 5 on the interval from negative 2 to 3 in brackets. If they exist, if they do not exist, state this and explain. So first of all, this function is continuous. There is no reason to doubt its continuity. It's a polynomial, it's just powers of x, meaning in particular that it's going to be continuous everywhere. There is no possibility of the numerator, a denominator being 0 or taking the log or a root of a negative number. So there is really no problem. So this function is continuous. So f of x is continuous. And the interval, let me just remind you of this interval notation. When we say negative 2 comma 3, that's basically the same. That's equal to x is between negative 2 and 3, including the endpoints. Literally everything on the real line between negative 2 and 3, including those little endpoints. So if you want to graph it, if you want to just do a graphic representation, even though it's strictly optional on the test, that's really all there is to it. So the function is continuous, and the interval, continuing here, is closed and bounded. It includes both numbers at the endpoints. That's really the idea of this problem. So if the function is continuous, which in this case it is, and the interval is closed and bounded, meaning it doesn't go all the way to infinity or minus infinity, it's finite in nature, it's a finite chunk of a finite length, and at the same time, it includes the endpoints. You have full circles here and here at the ends of the chord. Then you know by the extreme value theorem that the absolute max and absolute min exist. The problem statement says find the absolute max and absolute min of the function if they exist, and if they do not, state this and explain. So we know that we're not chasing wild geese, and we know for a fact that these things actually exist. What's the name of the theorem that guarantees this? So the extreme value theorem, EVT for short, guarantees that there are absolute extrema. There are absolute extrema. Parentheses, min and max. Okay. How do we go about finding these min and max that we know are guaranteed to exist? Well, one thing you got to do, the logical first step in any calculus problem that asks you to find the minimum and the maximum, is to obviously take the derivative that's actually provided to you, the function, sorry, that's provided to you out of the box, and just derive it first. Let's actually derive it. So let's derive the function. The function, I believe, is, let's actually write that down here. So f of x is actually equal to 2x cubed minus 3x squared, plus minus 12x plus 5. Okay, good. Now, let's actually derive this function. So derive f of x. What do you get? You get f prime of x is equal to 2 times 3 times x to the squared minus 3 times 2 times plain x, because it's x to the 1, minus 12. The derivative of plus 5 is simply 0, because the derivative of any number, constant number, not attached to a variable, is going to logically be 0, because it doesn't actually change. So f prime of x is going to be equal to 6x squared minus 6x minus 12. Okay, let's actually factorize this. F prime of x is actually equal to 6 times x squared minus x minus 2. Good. Now, we found the derivative. The logical next step is to actually solve for the derivative being 0 to find the critical numbers. So solve f prime of x equals 0 for x. And so you solve 6 times x squared minus x minus 2 as being set equal to 0. Well, I mean, the 6, no way, there's absolutely no way that the 6 is going to morph into a 0, so the 6 gets discounted. The only possibility of this product being a 0 is x squared minus x minus 2 is equal to 0. And so we can either use the quad formula or factorize if the numbers are lovely enough. You can do whichever you want. I'm just going to factorize. So, or decompose this. So x minus 2 times x plus 1. And that's actually be set equal to 0. So you got two possibilities for the whole thing, the whole product to amount to 0. You can actually have either x plus 1 is equal to 0, in which case x is negative 1. That's good. Or x minus 2 is equal to 0, in which case x is equal to 2. Good. But we're not quite done yet. We need to perform a little sanity check. The function in the problem isn't a standalone function living on the entire universe. It's restricted to this interval, meaning everything between negative 2 and 3. So x is between negative 2 and 3. So x is between negative 2 and 3. And if you actually look at these 2 points, both of these actually belong to this interval. Negative 1 is between negative 2 and 3, and 2 is between negative 2 and 3. So both critical numbers, oh, sorry about that, stylus got away from me, numbers, x equals 2 and x equals negative 1 belong to the given interval, negative 2 to 3 like this. And so we have to take both. We have to inspect, or we have to check both. Okay. We're almost done with this problem. We know that the absolute max and absolute min exist by the extreme value theorem because the function is nice and continuous. It doesn't have pieces or places where it can go haywire, like with a division by 0 or a log of a negative number or a root of a negative number. And the interval includes both endpoints, and it doesn't go all the way to infinity or negative infinity. That's beautiful. Now, the thing is we still want to know how to find the max and the minimum points. We know from that theorem in class, given that procedure for this type of problem, it's a standard type of problem template, we know that the absolute max and min can occur either at the endpoints or at those special numbers in between, the critical numbers where the derivative is 0. So now comes the final step before it's medal time, where we give the gold medal for largest value and the gold medal for smallest value. So the final step, we must now plug the critical numbers, which in this case are x equals negative 1 and 2. We must actually plug the critical numbers and the endpoints into the original function. You must not plug into the derivative. To find the y-coordinates or values of the function, you must plug into the function itself and not the derivative. So numbers and the endpoints into the derivative. That is important. I'm sorry, not the derivative, sorry. Silly me, into the function. Sorry, psych myself out. Into the function. Parentheses, not the derivative, that's what I meant. Not the derivative. Double underline this. When it's gold medal time to conclude or wrap up this problem, you have to plug into the original function. So f of x is equal to 2x cubed minus 3x squared. I'm just reminding you of the formula. On an exam, you would just scroll up visually to the top of the page. Minus 12x plus 5. Good. Now, I do believe the leftmost endpoint was negative 2. So let's actually plug in f of negative 2. F of negative 2 is, let's literally plug it in. 2 times negative 2 cubed minus 3 times negative 2 squared minus 12 times negative 2 plus 5. Okay, let's actually simplify this little expression. Negative 2 cubed right here is negative 8. So that's 2 times negative 8 minus 3. This negative 2 to the power of 2 squared is nothing but 4. So negative 3 times 4. This negative 12 times negative 2 is plus 24. And the 5 actually, of course, remains unchanged. So you got negative 16, negative 12, plus 24, plus 5. And so if you actually do the math, I do believe that's 29 minus 28, and so that's a 1. Highlight this value with double underline it, or don't box it, because box is usually more appropriate for the final answer. We'll see why I'm double underlining it in a moment. Now, let's actually plug in the right endpoint, which is 3. So I'm literally plugging in, replacing what I did above, only with the number 3. So f of 3 is 2 times 3 cubed minus 3 times 3 squared minus 12 times 3 plus 5. 3 cubed, this one is actually 27. It's 3 times 3, which is 9, multiplied by 3 yet again is 27. So that's 2 times 27. That's good. Minus 3 times 3 squared, this is 9, this is negative 3, so negative 3 times 9 is negative 27. Minus this one, 12 times 3, that's negative 36, plus 5. Okay, so 27 times 2, that's 54, minus 27, minus 36, plus 5. Good, let's see what we get. 54 minus 27 is 27, minus 36, plus 5. Good, oh, sorry about that. Now, the last piece is 27 minus 36. I do believe that's negative 9. So negative 9 plus 5, that means negative 4. Let's double underline this value. That's how I basically proceed with this type of problem. Now, that takes care of the endpoints. And let's actually look at the two critical numbers where the derivative is 0. Let's actually try x equals negative 1 now, plugging into the original function and not the derivative. F of negative 1 is actually equal to, that's literally this choice, x is equal to negative 1. Let's plug into the function and see what we get. 2 times negative 1 cubed minus 3 times negative 1 squared minus 12 times negative 1 plus 5. Good. So what do we get? We get negative 2, because negative 1 cubed is negative 1. That's easy enough. Now, negative 1 squared is just plus 1, so times negative 3, that's a negative 3. Negative 12 times negative 1 is plus 12. And this is a plus 5. So we got ourselves negative 5 plus 12 plus 5. That negative 5 plus 12 is 7. Plus 5 makes a 12. We're almost done, everyone. The only remaining point we need to plug in is the other point where it's actually 0, the derivative, which is x equals 2, this one. So let's plug in 2 and see what we get. F of 2, that's actually equal to 2 times 2 cubed minus 3 times 2 squared, yes, minus 12 times 2 plus 5. Good. Well, 12 cubed is going to be, 2 cubed is going to be 8, so 2 times 8, minus 3 times 2 squared is, of course, 4, minus 12 times 2, what's that? Negative 24, plus 5. Okay, good enough. 2 times 8 is 16, minus 12, minus 24, plus 5. 16 minus 12, that's 4, minus 24, plus 5, and that's going to be, 4 minus 24 is negative 20, plus 5, and that is equal to negative 15. Double underline this. So in this case, we got the two endpoints, and the 2 points, in this case it's 2 points, the 2 points where the derivative happens to be 0 on the interval. So we got count them, 4 values that are double underlined, and now comes the fun part. We must award medals. A gold medal for the largest value. So if we look at 1, negative 4, 12, and negative 15, what happens to be the largest value? Well, that's 12 amongst the double underlined ones. So that's the absolute max. That's the absolute largest value, absolute max. Now the gold medal for smallest value, you got the possibilities 1, negative 4, 12, and negative 15. Well, negative 15 seems to be the smallest such number here, so absolute min. Might as well box this, and might as well box this. And that takes care of problem 2. Let's actually move on to problem 3. Okay, everyone, let's move on to problem 3. A bus company operates a tour route that currently charges $20 per passenger and averages 400 passengers per day. Market research indicates that for every $1 increase in ticket price, the company will lose 10 passengers per day. Find the ticket price the company should charge to maximize daily income. Show that you have indeed found the maximum. Okay. So that's actually, there is some logic to the problem. The more you jack up your ticket price, the more passengers you're likely to lose. If you jack up your prices, people aren't going to be happy. They're going to look for a more economical alternative. So that makes sense. So the baseline, the actual baseline of this problem, pre-modifications, pre-tweaking and optimization, is $20 per passenger. That's the price of a ticket for a single passenger, and at 400 passengers per day. The problem's dynamic is basically that you jack up your ticket prices by $1 in each increment, and for each dollar you raise your ticket price by, you will lose 10 passengers per day. So for every $1 increase in ticket price, the company will lose 10 passengers per day. Okay, find the ticket price the company should charge to maximize daily income. Okay, so let's actually talk about what the variable in this problem is going to be. The one unknown, the one thing that's actually glaring and actually sticking out from this problem is we don't actually know by how much we should jack up our ticket price. We know the original ticket price, the baseline, is this $20 right here. So the base is $20. Now, logically, I want to jack up that price by a certain number of dollars. Okay, so let's actually call the increase in price X. So call X, the variable X, the amount you raise the ticket price. Okay. Now, what's the old price? This $20. You jack up your price by X dollars. So the new ticket price is 20 plus X, of course, in dollars. Okay, so that's going to be that in US dollars. In dollars. That's the number of dollars each ticket actually costs now. Now, how do we actually find the total income? How do we actually look at how much the stream of cash that the bus company is making? Well, the total income of the bus company is, what is this going to be? It's going to be the ticket price times number of passengers. Right? Yeah, number of passengers. Which is also the number of tickets, because each person has their own ticket in this scenario. So the number of passengers is logically the number of tickets. So if you sell a ticket for P dollars and you sell T tickets, for instance, the total price is P times T. That's also the formula for revenue we saw back at the beginning of the course. The number of units you sell times the price of each unit. This is not meant to be a business application problem, by the way. It's meant to be a word problem. So the ticket price is actually, we have found an expression for it. We know for a fact that the ticket price is this. So the ticket price is going to be this. So the total income, for instance, call it something like I, big I, capital I for income of X is going to be equal to the number of tickets, the ticket price, which is 20 plus X. That is going to be multiplied by the number of passengers. Now, what is the number of passengers? The number of passengers, is going to be what? The old number of passengers before we do our tweaks and our fancy optimizations was actually 400 passengers. Now it says for every increase, $1 increase in ticket price, the company will lose 10 passengers. Okay, so logically we want the 400, the passengers, the number of passengers, minus the number of passengers that we lose. What is the number of passengers that we in fact lose? Well, you lose 10 passengers for every $1 you jack up your price. But we've already denoted this number of increase in this amount of increase in dollars as X. So the number of passengers you lose is 10x. So your amount of passengers currently, the updated number of passengers rather, is 400 minus 10x. So your I of x, your total income, is going to be 20 plus x times 400 minus 10x. Okay? And so your I of x is going to be equal to, let's actually distribute these parentheses. We got the 20 times 400, that's 8,000. And you got the 20 times negative 10x, that's negative 200x. And you got the x times 400, that's plus 400x. And you got the x times negative 10x, that's negative 10x squared. Okay, and you want to maximize this function. You want to maximize this function. Maximize this function because you want to maximize your income. So maximize this function. So how do we do this? Let's actually simplify it. I of x is equal to, this 8,000 has nothing to simplify with, 8,000. We have negative 200x plus 400x, that makes plus 200x, minus 10x squared, right? Good. How do we actually simplify, how do we actually find the maximum of this nice looking function? Well, to find the maximum, derive the function, and equate to 0. I prime of x is going to be equal, the derivative of 8,000 is the derivative of a number which is 8,000, that's over and done with, it's a 0. The derivative of 200x is just the coefficient 200. And this little guy, the derivative of, sorry, that's 200. And the derivative of this little guy is negative 10 times the derivative of x squared, so that's negative 10 times 2 times x. So I do believe I prime of x is equal to 200 minus 20x. Solve. I prime of x is equal to 0 for x. And so you get 200 minus 20x is equal to 0. And so you can add 20x to both sides, and you get 200 is equal to 20x. Divide both sides by 20, and you get x is equal to 200 divided by 20, which is, I believe, if you cancel out, you get a 10. So it seems like what we suspect to be a maximum is a 10. The only problem is, how do we actually verify that it's a maximum? Remember, if the derivative is 0, that can also be a minimum. The problem instruction specifically states, show that you have indeed found the maximum. Show that you have indeed found the maximum. Show, as in convince the author of the problem. Now, let's use the second derivative, actually, the second derivative test. I prime of x is equal to this one. I prime of x is equal to 200 minus 2x. I prime of x is equal to 200 minus 20x. Good. Now, what's the second derivative? What happens when I derive this again? That's going to be, the derivative of this 200 is 0 because it's a number, and the derivative of this negative 20x is just negative 20, which is the coefficient. The second derivative logically seems to be negative. Now, if the second derivative is negative, the original function, big I of x, for income, is going to be a frowny function, not a smiley function. It's going to be concave down, meaning it looks like this. So if it looks like this, we have indeed found the maximum, because a frowny function's vertex point can only be a maximum. So we have indeed found the maximum. So we have shown the maximum using the second derivative. Let me just remind you, if the second derivative at a critical point is negative, like this means the function is frowning and it has a max. If the second derivative is positive, that means the function is smiling and it has a minimum. In this case, mission accomplished. We have indeed shown that it's the max because the function is frowning and thus it can only have a max. That's over and done with. But the problem statement asks us find the ticket price the company should charge to maximize daily income. We found the x. The x is indeed 10. That's a perfectly valid x. But the problem was asking find the ticket price. The ticket price is actually this one. New ticket price is 20 plus x. So ticket price, as you'll recall from the beginning of the problem, ticket price is 20 plus x. X is equal to 10, so logically plug in. So price is going to be equal to what? 20 plus 10, 30 bucks. If the company charges 30 bucks per ticket, that's going to bring its maximum, going to bring its daily income stream of cash into to a maximum. And that's over and done with for this problem. This is an optimization word problem. It's going to be problem 3 on the exam. Okay, everyone, let's start problem 4. It's the related rates problem. The length of a rectangle is increasing at a rate of 3 centimeters per second, and its width is decreasing at a rate of 2 centimeters per second. At what rate is the area of the rectangle changing at the exact moment when the length is 10 centimeters and the width is 6? Okay, let's actually denote the variables in this problem. On the exam, if something like this shows up, I would actually give you the formula, even though in this case it's simple. The area of a rectangle is nothing but length times width. So let's denote L as length, and let's denote W as width. Okay, so the area of a rectangle is of course length times width. Area is equal to length times width. And of course, this being a related rates problem, the variable x is now t. The independent variable, the atomic variable, is now t, because this kind of problem usually involves kind of a movie playback in time, if you prefer. So it's a of t is equal to L of t times W of t. You are by no means required to actually write this of t. This is kind of a safety feature of mine to prevent me making mistakes. I found it useful since I was a student. Just because now I'll remember that this is a product of two things, so when I derive both sides, which is always the step in this related rates problem, when you have an equation, you derive both sides, it's always good to remember that this is in fact the product of two functions. So let's derive both sides, in this case using the product rule. So derive both sides using the product rule. Derive both sides using the product rule. So a prime of t is going to be equal to literally deriving this, both sides of this, and plugging into the product rule. L prime of t times W of t plus L of t times W prime of t. Okay. The thing that we want in this problem is the rate of the area. So you want the area, the big A stands for area. And when we say rate in this problem, we actually mean the derivative. So this is what we want. What we want. Okay. Logically, this is the only unknown that's supposed to remain in the equation. As you'll remember, that simple logic of one equation, one unknown. Everything else in this equation has to be known. Okay, let's actually look at the problem statement. It says the length of a rectangle is increasing at the rate of 3. So the length is increasing at the rate. So let's cognate the word rate with the word length. So the rate of the length, if we combine these together, that just means L prime is actually equal to plus 3. Why is it not negative 3? Because it's increasing. Remember, if a function is increasing, in this case the rate is positive, that means the function is going up. So that's plus 3. Sorry, the stylus. Plus 3. Now, the width is decreasing at the rate of 2. So the rate of the width, if we actually cognate these two, since it's decreasing, that means that the width prime, the W prime, is actually not going to be equal to plus 2. It's going to be equal to negative 2. So W prime is equal to negative 2. The rate of change of the width, that is the derivative of the width, W prime is equal to negative 2. So let's actually move on to our little equation and plug that in. L prime is equal to 3. Let's just mark it. L prime is 3. And W prime is equal to negative 2. Spectacular. Now, let's actually ask ourselves, what about the W and the L themselves? What are the length and width? Not the rates, but the actual width and length. It says the length is 10 centimeters. So L is equal to 10 centimeters. And the width is 6 centimeters. So W is equal to 6. So W is equal to 6. And the length is going to be equal to what? The length is going to be equal to 10. Okay, so let's actually plug this in. So a prime of t, which is our holy grail, what we want, is actually equal to 3 times 6 makes 18. 10 times negative 2, these two, that makes negative 20. And so the final answer is negative 20. A prime of t is equal, I'm sorry, negative 2. A prime of t is equal to negative 2. I wrote it right, pronounced it wrong. Negative 2. What are the units? Well, the units, just to be proper, because it's a word problem, the units of length are in centimeters, so area has units of length squared, so, and this is the rate of area. So it's going to be units of area divided by time. So the area is going to be centimeters squared, and the time is given in seconds. It says centimeters per second. So the area is going to be in centimeters squared per second. And so, just to actually make sure that this is interpreted correctly, this is not an indication that you've done something wrong. If a rate is negative, that means the original quantity is decreasing. All this means is that the area of the rectangle is shrinking in time as opposed to blowing up or going up in time. That's literally all this problem means. If you solve the related rates problem on the final, and there will be one, and it'll also be problem 4 because it's the same topics as the mock in the same order, then just because if you get a negative rate, that's by no means something to second guess yourselves or something to cause you alarm. If a rate is negative, all it means is that something is decreasing. Remember, when the derivative is negative, the original function is decreasing. Perfectly valid, nothing to be concerned by. Okay, everyone, thank you so much. This concludes the first half of the mock final. We will now do problem 5. Okay, everyone, the next problem 5, is implicit differentiation, using implicit differentiation to find dy over dx, or y prime if you prefer, for the curve x squared y squared plus y cubed minus x is equal to 9. Okay. What's the logical first step in actually finding this? Well, you want to derive both sides. If left equals right, logically the derivative of the left equals the derivative of the right. So derive both sides. Derive both sides of the equation. Good. Now, on the left side, you got x squared times y squared. You want to derive that. So let's leave that as a prime for the time being before simplifying, or computing, I should say. Plus y cubed prime. I do believe that's that. Now the derivative, what's the derivative of negative x right here? That's especially simple. That's negative 1. Is equal to the derivative of the 9 on the right, and the derivative of a constant number not attached to a variable x or y, in this case, is obviously 0. Okay, now let's actually take care of these two building blocks. We got two primes. Let's take care of both of them, each of them one by one. You got this one, which is a product rule. So x squared prime times y squared plus x squared times y squared prime, literally me plugging into the product rule, plus this one. Now let me remind you of the derivative of not x to a power, but y to a power. So remember, this is the same formula for what you would call the generalized power rule. When you got y to the n, all of that prime, you get n times y to the n minus 1 times y prime. So if you actually take this formula in green and apply it to this little building block, what you get is, let's emulate the power rule, 3 times y squared, yank the 3 out and shave 1 off the power, multiplied by y prime. Multiplied by y prime, because that's what we have to multiply by, the inner derivative, this one, y prime, if you'll recall this formula from the lecture. That's equal to, that's minus 1 is equal to 0. Almost done, or almost done with this step, I should say. So what's the derivative here? What's this x squared prime? That's a simple x to the power. There's no need to worry about anything else. It's a classic power rule. So 2xy squared plus x squared times, what's the derivative of this y squared prime? Recall the formula in green. 2y times y prime. Good. Yank the 2 out to the front and shave 1 off the power. Plus 3y squared times y prime minus 1 is equal to 0. Good. Let's actually clean this up a wee bit. So that's 2xy squared. That stays the same, this one. This one is, I'm just going to bring the 2 out to the front because sometimes this 2, it's more convenient to have the numbers out in front. So it's plus 2x squared times y prime. Good. plus 3y squared y prime minus 1 is equal to 0. Good. Now, let's actually see what we need to do next. The calculus is now over. So this concludes the calculus. So the only thing left is to use algebra to solve for y prime. We isolate everything with y prime on one side and everything without y prime on the other. So let's actually see what we can do here. You got the y prime, this one, and you got this one. These two actually belong on one side. So let's actually keep them, I should say this one. Let's actually keep both of them on the left. Now let's transfer the stuff that doesn't have anything to do with a y prime, that just has numbers x and y's and powers thereof to the right. So what I'm going to be doing is I'm going to take this -1, migrate it to the right to make it +1, and I'm going to make this junk migrate to the right with a minus sign. So if we actually take a look at this, let me zoom out a bit so it all fits in the same view. So you got 2x squared y prime plus 3y squared y prime is equal to 1, because this -1, this one right here, when you migrate it to the right, you of course change the sign. That's high school algebra, so +1. And this little guy, 2x times y prime, migrated to the right, is going to become the same thing with a minus sign, so negative 2xy squared. And that's, if we actually look at that, we're almost done. Now comes the fun part. Take the left. It's always going to be this ultimate step. Always factor out the y prime. Y prime times 2x squared y plus 3y squared is equal to 1 minus 2xy squared. All you got to do is take this coefficient that's adulterating the y prime and divide by it. So divide by 2x squared y plus 3y squared. So you literally kill this, in the non-violent sense, of course. And that's actually equal to y prime. That's actually going to give you y prime is equal to 1 minus 2xy squared divided by 2x squared y plus 3y squared. And that seems like a perfectly valid final answer to put in a box. Okay, everyone, let's move on to problem 6, the U subproblem. Compute the indefinite integral, 6x plus 3 divided by x squared plus x plus 4. Now, another way of rewriting this integral is 6x plus 3, good, times x squared plus x plus 4, all to the power of -1 times dx. Remember, a reciprocal is just the same as -1. This is only optional. I'm just trying to emphasize something. What you want to do in this case is take the base of the power. In this case, it's category 2 because it's a power of -1, so you will literally take this, or if you prefer to look at the original equation, at the original integral, you will take the denominator. So that is going to be the u as the u sub. U is the base of the power. So that was just a visual aid. That was just an auxiliary aid where I rewrote the integral. In this case, you could just look at the integral and take the denominator. So in this case, what you want to do is you want to take this u to be equal to x squared plus x plus 4. And let's actually take the derivative of this. This is the first step to actually determine the u. Now, what's the derivative? Du over dx. That's going to be 2x plus 1. Flip it over, and you get dx over du is equal to 1 over 2x plus 1. That's good. Multiply both sides by du, and what do you get? You get, I'm going to zoom out a bit. You get dx is equal to 1 over 2x plus 1 times du. That's over and done with. 2 items on the checklist. Now let's plug back into the integral both of these. 6x plus 3 divided by u, the denominator is u. The 6x plus 3 on top is the dangling part, which will hopefully cancel if we've done something, if we've done our job correctly, which we have. The dx, basically the original integral had a dx, as it always does, and we need to multiply by that dx. So let's multiply by that 1 over 2x plus 1 du. Now, on the surface, it seems like now is a good time to panic because this 2x plus 1 doesn't seem to want to cancel with this. They're not exactly the same thing. But upon closer inspection, if you look at this, you can actually see that you can factor out a common term, 3. You can agree with me, hopefully, that 3 times, this thing is 3 times 2x plus 1. Literally factor out the common number factored. 1 over u times 1 over 2x plus 1. Cancel this with this, du, and you've got the ultimate lovely integral. Now, let's actually take out the 3 outside, because it's a constant. 3 times 1 over u du. Now, what's the integral of 1 over u? What's the integral of the reciprocal? That's the one exception to the power rule. You can't take the power rule because you would divide by 0. The integral of 1 over, basically 1 over a clean variable, is ln of the absolute value. So ln of 3 ln of absolute value of u plus c. And in this case, we must bring it back to the original variable. The author of the problem gave us the problem in terms of x, so we must stick to x and honor our commitment to x and give our final answer in terms of x. And so the u is actually equal to this junk x squared plus x plus 4. So in fact, 3 equals ln of x squared plus x plus 4 plus c. That seems like a good answer to put in a box. And this concludes problem number 6, the indefinite integral problem on the exam. Okay, now comes the turn of the definite integral problem. This is something we will see in class on Monday. That's basically the last building block you'll need to actually solve the final in its entirety. We will see that on Monday. So compute the definite integral, the integral from 0 to 1 of x squared over e to the x cubed dx. And there's a useful hint that this fraction can be written as this following product. So we might as well rewrite the integral using our hint. This is basically what's going to go inside the integral. 0 to 1 of x squared times e to the negative x cubed dx. Okay. This is a simple enough problem in terms of which u to take. Amongst the 3 categories, we have an exponential category, cat 3, because we have an exponential e to the power of something. So the u is going to be literally that thing that's on top of the exponential. So let's actually take u as the exponent or the power itself. U is equal to negative x cubed. Let's take du over dx. What is the derivative of this logically? It's negative 3x squared. So let me actually move this a bit to the left just so I don't run out of room. I apologize. So let's actually flip them over. Dx over du is equal to 1 over, if you prefer, 1 over negative 3x squared. Multiply both sides by du. That's pretty standard. It's always the first steps in the u sub problem. And so dx is equal to, I believe, negative 1 or 1 over negative, if you prefer, 1 over negative 3x squared, whichever you like. It doesn't matter where you move the minus sign. It's transferable, times du. Beautiful. You got this, the u, and you got the differential, the dx. We can now plug both into the integral. And actually get the integral. I'm purposely saving the numbers, the limits of the integration that go on the s sign. So this is going to be x squared. That's still the dangling part, which we will leave x squared. X squared. Multiplied by e to the power of u. Negative x cubed is u, so e to the u. Multiplied by 1 over negative 3x squared, just parentheses just to keep it nice and clean, times du. Now here comes the beautiful part. You can actually kill the x squared with this x squared, non-violently of course, and you can actually get the correct integral. E to the u times negative 1/3 du, which we can actually move the negative 1/3 out, times e to the u du. The only question remains, what happens to the numbers? Those limits of integration 0 and 1. Let me just remind you of something. In an definite integral, which is a specific number, where it does have those limits 0 and 1, what you actually want to do is take the indefinite integral that you would get, and you want to plug the limits into it. The only thing is that the original integral was given an x. So these limits actually stand for x equals 0. So let me highlight this. This means x equals 0, and this means x equals 1, because the original variable of the integral is x. So this means x goes from 0 to x goes to 1. So in this case, we want to translate the x equals 0 and the x equals 1 into values of u. So let's see how we do that. U equals negative x cubed. So for x equals 0, you get u is equal to negative 0 cubed, and that's negative 0, which is just 0. Anything times 0 is, of course, 0. That goes on the bottom. And let's actually see what goes with the top. The original top was x equals 1. So let's see what u becomes. U equals negative x cubed. So when I plug in x equals 1, what do I get? I get u equals negative 1 cubed, and that gives us negative 1. So the top one is negative 1. So the new integral, I am double underlining it instead of boxing it because it's not quite our answer. Our answer is supposed to be a number. So the original integral we want to compute is negative 1/3 times the integral from 0 to negative 1. 0 to negative 1 e to the u du. Okay, this seems simple enough. This seems simple enough because we have the integral of a clean e to the u, a e to the clean variable. And there is no x's and u's hodgepodged anymore. It's just a clean e to the u, so our u sub, our substitution was actually successful. So in this case, what's the antiderivative? What's actually the antiderivative or the primitive function or the ancestor of e to the clean u? It's e to the clean u. So it's going to be negative 1/3 multiplied by e to the u. And remember this little symbol which we will see in class from 0 to negative 1 in brackets. And so what this actually means is take the negative 3 on the outside, negative 1/3 because it multiplies everything. And in the parentheses we put e to the negative 1 minus e to the 0. And so what this means is negative 1/3 e to the negative 1. And just to remind you, e to the 0 is nothing but 1. Anything to the 0 is actually 1 in this class, except for 0, of course, which is undefined. So the point is e to the 0 is 1. So if you want to write it on an exam, it wouldn't be critical for full credit, but just so everything is nice and dandy. So this is 1. So this seems like a perfectly valid final answer to put in the box. Or let me just erase this and make a point inside the answer. So just a little note that e to the 0 is 1. And this seems like a very good place to stop. You can simplify this further if you want to, but it's by no means necessary, and at this point you're just playing with your math. So as far as correct final answer, both answers in the box will receive full credit. And just to remind you, when we actually have this little expression, when you have, for instance, let me just remind you of this notation. You'll see this in class on Monday. When you have, for instance, f of x from a to b, that's just a shortcut for saying f of b minus f of a. That's literally the same thing. You can denote it any way you want to, but instead of actually, if you want to give a preview for your answer like I did here, that's basically why this parentheses actually worked. You could have skipped these parentheses, but this is just good practice to make sure you don't forget that the bottom limit, the bottom number is 0, and the top one is negative 1. So this one is what you would call optional, but it's good practice. So that's a notation mathematicians came up with. It's good practice to clean up your work and to avoid any mistakes. I should know about mistakes. I tend to make billions of them. So that's it for this problem. Also, another way of writing this potentially is if you want to write it with a vertical bar like this, this also means f of b minus f of a, or any other variable if you like. Same thing for f of u for a to b, or f of u from a to b like this. Literally, it doesn't matter the variable. The point of those curly braces, those curly brackets, or that big bar with a on the bottom and b on top means plug in and subtract top minus bottom. That's all it means. Thank you, and we will now move on to the last problem, which is problem 8, to conclude this video. Okay, everyone, we have come to the end of our mock exam. Problem 8 is the last problem, the third integration problem. Suppose the demand function for a product is given by P equals demand D of Q is 100 minus Q squared, and the supply function is given by P equals S of Q equals 20 plus 2Q, where P is the price per unit in dollars and Q is the quantity in units. Compute the producer's surplus at equilibrium, Q sub 0, P sub 0, which is where supply and demand intersect, And recall, the producer surplus formula is this integral. The integral from 0 to q sub 0 of p sub 0 minus s of q dq. Okay. The first part of this problem is to actually find the equilibrium point. Find where supply and demand actually intersect. So you actually want to find this little guy, equilibrium. That's always the first step in this type of problem, which will show up on the exam with different numbers. So first step is to find the equilibrium point. So first step is always in the surplus problem. First step is to find the equilibrium point. How do you actually find that? You take this demand function and set it equal to the supply. So d of q equals supply of q. Supply and demand are equal. That's the point. What's d? 100 minus q squared. That is equal to s. And what is s for supply? 20 plus 2q. Unless I wrote it wrong. Yep, 20 plus 2q. Okay, let's actually solve this little equation. All I'm going to do is I'm going to make it a quadratic equation. In this case, I got a q squared, so I'm going to make it a quad equation, and I'm going to solve it for q. I'm going to do is I'm going to take the left side and migrate it to the right. Left goes to right, so I'm going to add plus q squared minus 100. And what do I get? 0 equals 20 plus 2q plus q squared minus 100. On the left, it's still 0, and that's equal to q squared. This guy. Plus 2q, that's this guy. Sorry. And 20 minus 100, this guy and this guy combined to form 20 minus 100 is negative 80. You can use the quad formula. Of course, on the exam, the numbers will be lovelier, or the functions will be even simpler. But the point is that you can either factorize, because it's nice numbers, or you can use the quad formula. I am going to factorize just out of force of habit. I'm going to do q plus 10 times q minus 8 is equal to 0. If you actually look at this, you got q squared, so you got minus 8q plus 10q, that's 2q. And 10 times negative 8 is negative 80. So the product 10 times negative 8 is negative 80. And 10 minus 8, if you add them up, you get plus 2. So that checks out. Good. What are the two possibilities? Either q plus 10 is equal to 0, or q minus 8 is equal to 0, q is equal to 8, or q is equal to negative 10. So on the surface, it seems like we got two possibilities, but we're supposed to only end up with one equilibrium point. Now notice the meaning of Q. Q stands for quantity. It's the number of units of a product. Q is the quantity in units. So if your company is in the business of producing phones or laptops or any other product or cars or whatever, there's no such thing as negative 10 phones or negative 10 bags of popcorn or negative 10 bags of chips. This one doesn't work because it gets discounted. Or disqualified, I should say. So disqualified would be the better choice. So disqualified because Q is positive. In this type of problem, Q and P are always positive. I'm going to make that clear in class. But Q and P, please let that be known right now. Q and P are always positive. And supply and demand, Q and P, at least in our course, economists might disagree, but Q and P are always positive in our world. Okay? So we found the Q sub 0. The Q sub 0 is where they intersect, and the only possibility is 8, which is indeed positive. So that's what's left. So the equilibrium Q, so equilibrium, Q sub 0 is equal to 8. How do you find the P sub 0? Remember, the equilibrium point, this one has Q sub 0, which we found. We still need to find the P sub 0. How do you find the P? Well, you take the Q that we have just now found, which is 8, and you plug it to either this thing or this thing. It doesn't matter which, logically, because they're both equal at that point. It's sort of like intersecting two functions or two lines, finding the x where they intersect and plugging into either one to find the y. The whole point is that they're both identical at that point. So let's actually plug into the s function just because it's simpler. So s of q is equal to 20 plus 2q. S of q is equal to 20 plus 2q. So S of Q sub 0, remember, the full name of this little guy is P equals S of Q. This thing is right here. Right here, that's P equals, because it's, you plug in the Q and it spits out the P. So S of Q sub 0 is going to actually be equal to, or the P sub 0 is going to be equal to S of Q sub 0, which means, plug back in, 8, 20 plus 2 times 8. What does that mean? 20 plus 1, 20 plus 2 times 8 plus 16. That gets us a 36. Okay, so we found the equilibrium point. That's most of the job done, I would say. So you found the Q sub 0, the balance point, the equilibrium point where supply and demand intersect to be 8, and the P sub 0 to be 36. Good. So far, so good. Now, what do they actually want us to compute? They want us to compute the producer's surplus, which they were nice enough to actually provide the formula for. So the producer's surplus is this one. This one given to you in the hint, and it'll be given to you on the exam. This formula for this corresponding problem will be given to you on the exam. Now, what we want to compute actually is, so what we want to compute is the formula given. What we want to compute is what? Is 0 to Q sub 0. That's the integral from 0 to Q sub 0 of P sub 0 minus S of Q times dq. Let's actually start plugging stuff into the integral. The Q sub 0 is 8. The P sub 0 is 36. And the S of Q, just to remind you, the S of Q is going to be equal to what now? It's going to be equal to 20 plus 2Q. That's given in the problem. Let's actually plug into the integral and set it up. So you got the integral from 0. What's Q sub 0? That's going to be 8 times, I'm sorry, inside the integral is going to be P sub 0, which is 36, minus in another nested set of parentheses, the SQ, so minus 20 plus 2Q. The minus applies to both terms in the supply function, dq. Okay, so let's actually touch up the integral and clean it up. You got S to 8 of 36 minus 20 minus 2Q. All of that is equal to dq. I'm sorry, multiplied by dq, sorry. So 36 minus 20, we might as well clean that up to 16. So it's the integral from 0 to 8 of 16 minus 2q dq. This is not a U sub problem because it's just powers and constants. There is no disgusting fraction or high power of a big expression or e to the something nasty. This on the exam will also, this corresponding problem will also not be a U sub problem. No need to do a U substitution. You will literally compute this integral as is and plug into it. And of course on the exam the question will be easier and the numbers will actually be easier to work with and lovelier, quote unquote, even though there is no fractions here, just integers so far. So far so good. So let's actually see how we can actually do this. What is the antiderivative of this? So let's find the antiderivative of this. What's the antiderivative of 16? That's 16q. The variable of integration is q. So a clean number is 16 times q minus 2 times q squared. Remember, this is q to the 1. Q plane is q to the 1. So jack up the power by 1 and divide by the new power. And that gets plugged in. The limits get plugged in from 0 to 8. Now, if you actually want to simplify just a bit before plugging in, because when you're plugging stuff in, it makes sense to simplify, because when you can get rid of this 2 with this 2, and you get 16q minus q squared in parentheses. I don't really care how you present your answer. You can also use this, instead of square brackets, you can also use parentheses for, but it's more mathematically proper to write square brackets, but on the exam, as long as it's unambiguous and I can read it, you'll get full credit. So from 0 to 8, so you basically plug in. So let's plug in the top limit, 16 times 8 minus 8 squared. And that's going to be minus 16 times 0 minus 0 squared. Well, logically, anything to do with 0 multiplied by 0 or 0 squared, this little guy is just a 0. So it doesn't add or contribute anything. So this thing is just a 0 equal to 0. Now, this is the only one, this is where the money is literally, because we're computing a business type quantity, or a quantity from econ. So 16 times 8, I believe that is going to be 128. Minus 8 squared, that's minus 64. And so together that makes 128 minus 64, so that's 64. And if you want to be proper, this is asking you for the consumer surplus. This is producer surplus. So if you want to give your final answer verbally, so producer surplus is, the producer surplus is 64. As long as I see the final answer is 64 and the work is correct and all there, you can expect full credit. This was a challenging problem. On the exam, the corresponding problem will have easier functions and numbers, and the algebra will also be simpler. The point of the matter is that problem 8 is going to be the last integral problem, and it's going to involve no u subs. As you can see, this integral involves nothing but powers and constants of the clean variable q. No fractions, no roots, no e to the nasty stuff. The point of the problem is to actually compute a basic integral, but it's your job to kind of set it up by plugging into the formula and running the machine to put together the infrastructure. Let me just remind you of something before we conclude. Something I was asked about in class, the integral of a constant. So the integral of a constant, integral of a constant, I mean fixed number, k. The integral of k times dx is kx plus c. Why is that? Because you basically want to find the antiderivative of k, and the antiderivative of a number k is basically the function such that when you derive it, you get k. You can agree that this line always has slope k, because the derivative, the coefficient of x, is the slope k. So that's basically how you can do it. If you want to see the more proper explanation with the power rule, you can also, this is not necessary, but it's something good to know. This is k technically times 1 dx, and k times 1, that's k times x to the 0 dx. So on this you can use the power rule, which is k times x to the 1 divided by 1 plus c. Both, because power of 1 and division by 1 give you the same thing. So that's basically two ways of seeing this. I will make it a point to emphasize this in class, but for the time being, please remember that the integral of a constant, a number like this, is kx plus c. So the integral, for instance, of 5 dx, not 5x, 5 dx, 5 clean, is going to be 5x plus c, or any other number for that matter. Thank you so much for watching me today. This mock exam has certainly been challenging. It's not meant to be easy. Overall, I think the level of difficulty of this is more than the actual exam you will see next Thursday. So this is good to be over-prepared. And thank you so much for watching until the end. Of course, you're always welcome to send me an email or talk to me about Zoom meetings or anything you like. And I will try my best to help you to the best of my ability. We will have a 2-hour review session in class on Wednesday where you can ask as many questions as you like. And I have office hours next week from Monday to Wednesday. Thank you so much. Best of luck. It's been my pleasure having you as my students, and I hope you enjoyed having me as your instructor. I wish you the best of luck in your endeavors, and you're always welcome to contact me in the future if I can help you with anything at all, especially if it's related to something quantitative. Thank you so much, and take care, everyone. Goodbye.